Okay, footfall analysis. Footfall analysis is basically prediction of how lively the floor structure is going to be. It's a vibration analysis, and vibration. Vibration comes in many forms, has many effects on the structure. It could be such that it actually damages the structure. I mean, you could get overload or fatigue. This could be an earthquake. It could be wind-induced vibration, such as the famous Tacoma Narrows, or infamous, I should say. It could be merely serviceability, discomfort. Floor's a bit bouncy. Building sways in the wind. Ride discomfort. If on the train or something like that. Noise coming through the structure. Machinery operation. You could have a compressor rattling the floor. Or alternatively, you might be operating machinery which needs to avoid vibration, such as manufacturing, high precision manufacturing, medical, operating theatre, for example, very strict on their vibration. Let's face it, you don't want when the lights shaking around, or whatnot, when the surgeon's trying to do brain surgery, or of course laboratories, electron microscopes themselves, optical microscopes, and so on. All sensitive to vibration, and these have quite strict vibration requirements. Now we're looking at footfall vibration today, so that's sort of a subset of those. I mean, GSA has the ability to look at all these, or most of these vibration checks, but we're looking at footfall. Footfall is human-induced vibration. Vibration caused by people walking around on the floor and shaking the floor plate accordingly. Like the cartoon, XKCD, but strictly speaking, that's a harmonic analysis rather than a footfall. But the principle's the same in many respects. So, footfall vibration itself. So, what we're looking at is footfall from vertical vibration. So it's not Millennium Bridge type vibration. Millennium Bridge was essentially a horizontal footfall phenomena, where you got phase locking of crowds walking. If you get horizontal vibration, you have to walk in step with the horizontal vibration, which means you then get a feedback between the people walking and the bridge, and everything gets worse and worse and worse. Vertical vibration is something different in that you do not have to walk in step with vertical vibration, and therefore you do not get the phase locking or the feedback loops that you can do with horizontal vibration. There are papers available if you do have a horizontal vibration problem that you need to look at, and I can soon send you references if you are interested. So, footfall vibration itself, what is it? So if you consider the bridge there, a simple beam, and somebody's walking across that bridge, every time they take a step, their foot hits the surface. That imparts a force and energy into the system, and these forces can start the structure to vibrate. Let's see the vibration mode there. And because there is damping in the system, it's not a perfect structure. There are connections between steelwork, there are cracks in the concrete and so on, various bits in there to absorb the energy, so the vibrations die off or reduce over time. Now there is more than one vibration mode. The first vibration mode, the whole bridge, the whole beam, whatever, moving, but you also get higher frequency vibration modes occurring at the same time. Now the diagrams are mode 1, 2 and 3. These are 3 of the modes which have been separated out. So you can see them individually, and they each have their own frequencies, but they're all happening simultaneously. And if you can see the video below, this is a GSA analysis of multiple modes actually working simultaneously. If you can't see the video, I'm not sure if the GoToMeeting will actually show it through, but it will show on the recording. We'll get to that. Now, that's the individual mode of a single beam or simple beam. When you go onto a floor plate, the modes become much more complex because obviously you're dealing with a two-dimensional plate rather than a one-dimensional beam. And you can see an example there of a vibration mode on a moderately complex floor plate. Now, once you have the vibration modes, you then need to do a subsequent analysis to calculate the velocities, accelerations and response values of the floor. The response values might be, the velocities might be calculated in terms of peak velocity or root mean squared, RMS, or root mean cubed on the floor, depending on the design guide and what exactly it's asking for. And likewise, accelerations might be in terms of meters per second squared, or it might be in terms of percent g in the design guide. I'll lead you through what sort of figures you're actually looking for. Now, I think most people are familiar with accelerations and velocities, but they often talk about a thing called response value. Now, a response value is acceleration, but it's acceleration compared to this ISO base curve for the limit of human perception. So for any given frequency, an acceleration of twice the values on that curve will give you a response value of 2. Values on that curve, response value of 1. Let's say if we had at a frequency of 1 Hz, acceleration of 0.1 meters per second, that would be a response value of 10. It's 10 times the base curve. Thus, our response value is dimensionless, but it's a dimensionless form of acceleration. Now, what response value you need depends a lot on what the structure is, what people are doing on that structure. For example, when people are lying down, they are very sensitive to vibrations, but if they're standing up, they're least sensitive. Likewise, if they're sat down doing something very delicate and careful, they are very sensitive. If they're walking across a bridge in the open air, they don't mind a bit of vibration. If you have a slender footbridge, then people expect a bit of vibration. They're quite happy with it. With a floor plate, they expect it to be a bit more solid, and feeling vibration is less acceptable. Hence, the target response value really depends a lot on what the structure is being used for, and these response values can range from, say, 1 for an operating theatre right up to 64 for a staircase or a bridge. The response of the structure to footfall is not just dependent on the frequencies. The frequencies are really important, but also the mass of the floor. To be more accurate, the modal mass. So, keep it simple, the modal mass is essentially the amount of structure which is moving as a consequence of the vibration. So if you take mode 1 there, the modal mass of mode 1 is going to be about half of the mass of the beam as a whole, because in the middle of the span, the whole of the beam is moving. At the end of the beams, there's no movement at all. and so some of the mass which is moving and so on, you come up to half the original, the actual weight of the beam. The other modes, you're getting different calculations on the modal mass. And the modal mass is important because we're looking for accelerations on the floor. The footfall, the heel impact, imparts a force into the structure, and you divide that force by the mass to get the acceleration out. Greater the mass, lower the acceleration. Now, because of this, so it's not so much the frequencies which give the acceleration. So, for example, you could have a short beam, and being short naturally got a high frequency, high natural frequencies, but because it's short, it's got a low modal mass, and therefore can give high responses. Conversely, you can have a very large or long span beam which has a low natural frequency, but because it's large, it has a high modal mass, and therefore has potentially a low response value. There's thus not a direct relationship between the frequencies and the response, though the frequencies do go into the calculations. Now that's simple beams, but again, you just remember when you're dealing with a floor plate, the modal mass is a lot more complex. For a single bay isolated, the modal mass is about a quarter of the self weight of that bay, but you can see when you get to vibration mode, you do get that mode is sort of tying into adjacent bays. That example there on the screen, that's an irregular or an isolated bay, which means it doesn't really grab much of the surrounding floor, which means the modal mass of that particular mode will be relatively low, and so you tend to get some quite high responses on these irregular or isolated bays. Conversely, when you've got irregular bays, these tend to have vibration modes which tie into lots of additional bays, and that increase the modal mass and lowers response. So the more bays you have, the wider the floor plate, the lower the responses, which is the reason why when you're doing a footfall analysis, you need to model the whole floor, not just a subframe or a single bay to get the right results. Conversely, you do occasionally hear the fallacy that irregular bays do not have a vibration problem. That is unfortunately complete rubbish. The isolated bays tend to have the worst vibration problem. It's just that they're difficult to calculate without finite element analysis. We should look at that example later on. Now, there are two types of vibration that you experience on the footfall. There's resonance and transient response. Now, resonance is when the vibrations build up over time. So if you look at this floor level, it vibrates over time at a particular frequency. And somebody comes along, and if their footsteps land on the floor in time with the vibrations, then those footsteps will gradually increase the amplitude of the vibration, and you get resonance. You get a build up from that person walking around. Now note this is the first harmonic, so this is the footfalls landing at the same frequency as the floor. And generally for buildings anyway, the design guys say that the first frequency should be usually about 3 Hertz or more, and people walk typically up to about 2.5 Hertz, which means you don't get the first harmonic vibrations on buildings, though you do on bridges, because bridges can be vibrating down to 1 Hertz or maybe even less. So you can resonate with the first harmonic. You can resonate with the second harmonic. If the floor frequency is twice that of the footsteps, then you'll get resonance on every other cycle of the floor. You can also get resonance on the third harmonic and also even on the fourth harmonic. Tend not to analyze beyond the fourth harmonic because including people here, it's very difficult for a person to actually walk with that regularity of step to cause resonance beyond the fourth harmonic. In fact, the effects of these harmonics are taken into account. They have less influence to get up the frequencies. Now, if this resonance was unchecked, the reduced vibrations would eventually destroy the structure, a bit like Tacoma Narrows. But thankfully, as I mentioned earlier, the structures do have imperfections built into the structure. Now, these can be accidental, sort of generic imperfections such as steelwork connections, concrete cracking, and so on, or they can be physical dampers built into the structure, deliberately there to absorb the vibration, a bit like you have on your car. And this damping absorbs the energy, and there's a thing called critical damping. And if the damping level is at the critical damping, you give it a displacement, and the displacement will reduce back to zero in the shortest possible time. For general structures, you are actually looking at a much lower value, and a building structure has a damping typically between 1% to 4% of critical damping, which means there is damping happening, not very much, and the structure then oscillates and overshoots and so on. Now, this damping level has quite a significant effect on the response. You can see there, for a low damping, 2% damping, getting a very high amplitude. 5% damping, it's considerably less, and so on. And this graph, you can see, it's, if you look at the horizontal axis, excitation frequency over natural frequency, so you go from static loads, where there's no amplitude at all, to resonance when the excitation is sort of tying in with natural frequency, and then beyond that when the excitation is just too fast to actually have any sort of interaction with the vibration modes. Now, this is a slightly simple view. If we look at an actual analysis results, you can see that you get the biggest response when the excitation frequency, the walking frequency, ties in with the structure, but you also get responses or resonances occurring at twice, at 3 times, at 4 times, and so on, in multiples of the walking frequencies. You can see there the damping does have a large effect on that. Or if we sort of zoom in a bit, if we take the first mode off, because the first harmonic, of course, we don't get that in the building structures, you can see there in a bit more detail how the footstep frequencies interact with the natural frequencies of the structure. So that's resonance. There's also called transient or impulse loading, and here you tend to have a very high frequency floor where the vibrations die off before the next footstep lands, so you don't get resonance, you don't get a build up, and the results then are purely about that first initial deflection and accelerations from the footsteps. Thus, damping has no effect on the transient response, because the damping has already reduced it, so you're preventing resonance. Guidance on footfall vibration. There are 3 main guides out there. The American Institute of Steel Construction documents released back in the 90s, left, and the more recent ones, the Concrete Center method, also known as the Arup method, and the Steel Construction Institute methods, are released in the last few years, and these tend to be the ones used, at least in Europe. America still tends to use the AIC guide for the time being. It's probably due for a rewrite shortly. There is also a Eurocode for footfall vibration at early draft stage at the moment, and looking forward to seeing more of that later. Some of the guides have what we call a simple method for calculating the footfall response. So this is a hand calculation type thing where you take your structure, you equate it to a typical bay, as they indicate in the guide, calculate the deflection, and from the deflection you can work out the fundamental frequency, and then get an idea of the response. But it's only an idea. The accuracy of the simple method is very low, and the modern guides all recommend that you actually use FE analysis to get accurate results. There are a couple of programs out there which claim to do footfall analysis. The vast majority of them only do this simple method, and the simple method is only an approximate guide. It's not at all accurate. And so if you've got something where, if you've got a case where the footfall response is crucial to your design, the simple methods will not help you. When you're doing the FE analysis method, which of course GSA does, what you're looking at is an FE model of maybe the floor structure if you're doing a building, or the whole structure if you're doing a staircase or a bridge. And having got the subframe analysis or model, as you need to find the various modes, and you can see the modes on this floor plate similar to the individual beams, but you see they're a bit more complex. Loading as well, you need to include the loads, you need to include all the credible dead loads plus some of the live loads. Unlike static analysis, it is not conservative to take maximum loads. If you take all dead and all live, you'll get a lower response because the mass resists the accelerations. But conversely, if you had a floor plate and you took no live load at all, that would be a condition in an empty office building, and who cares if an empty office shakes a bit? It's when there's people in there. So generally the guides say take 10% of the live load for a floor, or alternatively virtually nothing for a staircase or a bridge. Again, the difference between static analysis and a vibration analysis is that for a steel case, for example, these beams might have simple or pin-ended connections in reality, but when looking at footfall vibration, the strains are very low, which means that the bolted connections don't actually get to slip, and therefore they all act as if they're fully continuous. So the analysis, footfall analysis, you don't model pin connections unless it really is a pin, like a roller or something like that. Conversely, you can also take a different stiffness value for the concrete. Concrete stiffness is very time dependent, and you're all familiar with short-term and long-term E values or Young's modulus values. For a dynamic case, the E that you can take is even less or greater than the short-term load. The SCI and the concrete centre guides recommend 38,000 newtons per millimetre squared for the Young's modulus. The Euro guides coming out recommend a 10% increase on the actual short-term stiffness. Is the drafts do at the moment. Another difference between static analysis and vibration analysis is what you do with cladding and walls. Under static analysis, that edge beam there will be supporting the cladding. under a footfall vibration, the cladding is supporting the beam instead, because the cladding acts as a very deep beam on the edge of the structure and prevents any movement really on that line, which means, as far as analysis is concerned, you just pin the edge. Obviously you pin it in the vertical direction, but pinning it in the horizontal direction also has the advantage that because the footfall vibrations, we are only interested in vertical movement on the floor, those horizontal restraints just prevent those horizontal modes of vibration. If you're doing whole building seismic, completely different case, obviously. So let's have a look at GSA itself in action. Now, first one I'll look at is a concrete model. This is this is a flat slab structure, and we already have it set up so that I have cladding restraints around the outside. I've got core in this corner here, and for a core I've actually got moment restraint on those nodes. The columns are modelled in, and these are all half the height to the next floor, with a pin at the end of those. I've also included super dead and live loads on this floor. So the first thing we need to do is do a new analysis task, and it's going to be a dynamic modal analysis. Now, we don't know yet whether this is going to be a high or low frequency fault, so I'm just going to ask for one mode to begin with, just to see what the floor is like, and I'm going to ask for a permanent variable. I'm just going to take 10% of the live load. And low frequency floor is the first mode, is less than about 10 Hertz. Remember, people walk speeds up to about 2.5 Hertz, so low frequency floor is vibrating less than 4 times the walking speed. Vibrations above that that's a high frequency. Let me just analyze this, and you can see that if I turn it on the vibration shape and look at the deflections, we can see we're getting a mode in this corner over here. Now, don't worry about the deflection. The deflection's reading 1 meter. The modal analysis is calculating the vibration shape and the frequency. The actual is not actually calculating deflection. It's just that for display and so on, you need to have a maximum deflection, so it's just set to 1 meter. It's called normalized. But frequency of 4 Hertz, this is a low frequency floor, so I'm going to delete those results. I'm going to call up that analysis task again, and I'm going to say I want modes up to, in this case, 15 Hertz. I'll say just over 15 Hertz. I'm not sure how many modes, so I'll just ask for 20. Now, what GSA will do is it will try to calculate 20 modes, and once it reaches this cutoff limit, it will stop. Analyze that, and we can see it's analysed. This value here, this just looks at the movements, the mass movements in the X and Y and Z direction. You can see we've only got vertical movement on this floor, which is great. No errors. Let's look at these modes. So we asked for 20 modes, it's given us 10. So mode 1, mode 2, mode 3, 4, 5, 6, see as the frequencies increase, the modes get more complex, and we see mode 10 at 14 Hz. That's fine. Now, if you want to make sure you get enough floor plate, you can envelope these modes. And I'll take 1 to 10. And you can see there from the red zones. So we've got all the significant areas. If you're interested in vibration footfall in this area here, we might need to push the number of modes up to make sure we've got definitive answers in this area, but that looks okay for me. I will now run a second analysis, so it's a dynamic response, and in this case we'll do a footfall. There are other dynamic responses which we can look at if you wish, but the footfall we'll concentrate on today. And under footfall we have a number of choices. Now, first of all, you can choose which mode. We've only got one dynamic analysis in here. Excitation method. Self-excitation is excite the response node only. What this means is for all the nodes we want to calculate the response at, self-excitation means we excite that node and then measure the response purely at that point. Whereas if you're doing a full excitation, you excite a node but measure the response everywhere. This means a full excitation is a sort of considerably larger analysis. So if you had 10 nodes, self-excitation 10 calculations, full excitation 100 calculations, and so on. Because the full excitation can be slow, we do have a shortcut method there called the fast. And generally what you do, we're going to do run the self-excitation first to make sure everything's working, and then maybe ramp up these methods until you get to the rigorous method, which so you see self-excitation very quick. Full excitation can take a few minutes or longer. It could be time for a cup of coffee or maybe lunch, depending on the size of your model for full excitation. I'll come back to this choice of response nodes. Damping ratio. You can get the damping in from outside, but we'll just concentrate on setting the damping mode, and the guys have various recommendations on what the damping value should be for your floor plate. Number of footfalls. For resonant response, the number of footfalls, the footfalls we build for a general floor plate, 100 is a good number. For something small like a staircase, you might feel justified taking a smaller number than that. So you'll probably find once you get more than 20, you'll probably get full resonance anyway. There's the weight of the person walking, and there's also the analysis methods, the ARAP or concrete center methods, the SCI methods, and the American AIC methods. Also got staircase as well as floor methods, and each of these has different forcing functions, but also different walking speed recommendations. I'll take the ARAP concrete center methods and just analyze that. Slight warning that says I should have modes up to 15. It's a warning. I'm happy with that. So let's have a look at the footfall response. And don't look at deflection. I'm looking at the response. Now, the response is all calculated at the nodal locations. You can see in this floor plate we're getting a response up to 9. Now, the transient response, say 4.5, resonant is 9. This is low frequency floor. Resonant results are dominating. But these dots is quite hard to see. So let's do the next option down, which is nodal results on elements. This takes these nodal results and smears them onto the 2D elements. So if I look at 2D elements, nodal results on the elements, you then get some nice contours which are much easier to understand. So we have response factors, but we also get RMS and so on, velocities, or peak accelerations, which is the critical frequency and the floor plate and so on. So there are various results you can get out of here. You can also get the results from the output section. So if we look at node results, let's say Footfall Induced summary, you can see we get the worst case for all the various nodes, and then right down the bottom you see we get the maxima, which is all at node 113, response value of 8, which if I tuck that over to the side and turn this one over there, I suspect it's on those two. Let's see. Find node 113. There we go. See that across there. That is the worst spot. Now if we look at node 113 in a bit more detail, let me just reduce this down, but now ask for detail of node 113. We can see that node 113, this is the peak acceleration, where the vibration is coming from, and so on. So a simple concrete model. How about some touch more complicated, which is a steelwork model? Now, this steelwork model, it's already been broken down, and you'll note that because the calculations are all done at nodal locations, including the massive lumps at the nodal locations, I've broken each span down into 8 pieces, so we get sufficient density of nodes where the calculation is carried out. At the moment, everything's on the centroid, so if we were to analyse this, this would be acting just as if it's a non-composite structure. Let's do that. Let's set up the analysis on this, and let me just make sure as well. We do have a dynamic concrete material which we are using. So yes, so the concrete is using the dynamic concrete method. So let's do a modal analysis. And again, let's ask for 20 modes. Upper cutoff 15 Hertz. Include dead and live loads. And let's analyze that, and we get, right, we click on individual modes, there'll be similar shapes, but if I look at the global dynamic summary, we can see we're getting frequencies 4.6 Hertz and above. Now, if this is going to be a composite structure, let's make this composite. So first of all, we need to offset elements. So I'm going to select all those beams, and I'm going to offset all those beams so that the top of steel is level. Use the tool, apply offsets, offset beams to align top surfaces. They're all now offset down, and I'll also find all the slab elements. Now these are 150 thick, so I will offset those. I'll offset them all up by half the depth. These will now all act compositely with each other. So on static load, the beams will go into tension, the slabs go into compression. And remember, the first frequency was about 4 Hertz. If I reanalyze that, summary, you see the frequency, it's more stiffer now, frequency went up to 5.9. Now, the new feature in the latest GSA, where we've actually just introduced a new option on the modal dynamic analysis. It's not defaulted yet. If we go into the advanced features, you'll see that we had the Jacobi subspace iteration previously. We've now got subspace iteration with shift locking. The effects of this, that you won't notice it too much on this model, is actually to speed up the analysis quite considerably. Bigger models, it can be analysing in like a tenth of the time of the previous methods. So it's not defaulting yet, but I do recommend that you have a go with that. Right, there's a floor. Now, floors, of course, you only really get horizontal vibration, but if we look at a staircase, now staircases, due to their shape, will tend to have horizontal vibration modes in there as well. Now, if we were to analyze this, now I've set this up so we can include or exclude the balustrading. The balustrading can have quite a significant effect on the vibration characteristics of a staircase. It's non-structural, but it does stiffen things up. So if we just do a modal analysis, let me just do one mode for the moment. And look at the vibration. Oh, let me just set the display so it ignores the balustrading. You see we are getting a significant mode on that staircase, which is coming in at 21 Hertz. Along that edge. But if we delete those results and reset that analysis so it's picking up the whole stair, now the first mode is actually now lower, but the vibration is really looking at the balustrading, and we need to get considerably more vibration modes. Let me just check, are we? Yes, we have read the new method. And the first frequency when the staircase itself starts to vibrate is, there we go. Now the first frequency there is about 75 Hertz on there, because the balustrading acts like a deep beam. If we now run a footfall analysis on this, now the footfall, we're not interested in footfall on top of the handrail and so on. So what I've got is a list of nodes which just pick up the treads themselves. And so we can do excitation of just the treads. People don't walk up and down the handrail. They're not interested in the vibration of the handrail. And so we're getting a response factor of about 35 on this staircase, which you can see is quite a lot higher than the floor plate, but probably still acceptable. Now, apart from excitation, on a point, let us look at effects of one place on another. Now, this is a irregular floor plate, which if I switch on the solids and switch the slab back, you can see this has quite a lot of irregular bays in there, lots of different spans and so on. And the standard methods can only cope with these sort of areas here, cannot cope with these bits here which don't quite tie in, these bits over here which are triangular, and so on. But the footfall responses, if I go and call up the responses for this structure, and controls one like that. Size the beams. Actually, let me switch those 2D elements off altogether, so it's a bit easier to read. Okay, you can see that the regular bays, the footfall is moderate, 5 to 6 or so on, but we're getting much higher values, 8, 9, 10, 11, 12 in some of the other areas, particularly next to this void. These would be areas where the simple method just could not touch. Now, if we were doing, say, an operating theatre, now operating theatres are interesting cases where they're very strict on the vibration, but because of the nature of the environment, people tend to be walking around slowly in them, which means the impact forces are lower. But there could be a corridor outside the operating theatre where people are in a hurry. So let us suppose that, let's say this corner down here is going to be our operating theatre. And what I will do is I will select those nodes there. Actually, let me just switch the results. Just switch the contours off for the moment. Oh, and the limits back on again. Okay, so these nodes here, which I've selected, I'm going to say this is going to be our operating theatre. So I'm going to right click and save those as a list, and I'm going to call them theatre. And I'm going to define the corridor outside, and holding the control down, I can toggle those ones off and toggle some of the other bits on. And right click and save that as corridor. So the responses in these areas response in the theatre, so I'll say self-excitation, response nodes, theatre. The walking speed is only 1.8 Hertz in this localized area. And we'll just analyze, that's done. And I'll do another analysis, which is fast excitation. So the response is again the theatre, the excitation is the corridor. The walking speed there is actually 2.2 Hertz. Analyze that. Slightly slower, do a few more calculations. Two-thirds away there. just reduce my display down to the operating theatre so it's easy to see. So remember the footfall response, if I call for actual values. So the footfall response in that theatre, 2.5 Hz walking speed, 10.3. If we look at the walking in that theatre with the reduced speed down to 1.8, the frequency comes down to 7.5. If we look at the respect of the corridor on that theatre, the response comes down to about 2.7, which means, again, in this particular case, it's the people walking in the theatre which is governing rather than the corridor outside, but you do have that ability to see. And in fact, we can see if you take this node here, for example, remember the outputs is at 2871. Let us look at, so what is causing that node there to vibrate? So let's look at resonant and transient response. So give me a summary. The case list is going to be the corridor. The node list was, let's select that somewhere. 2871. Yeah, so we can see node 2871, the response is critical vibrations coming from node 2763, which if I find 2763 and sorry, what was it? 2871 2763. One, 2673. Did I get that right? 2763. There we go. So response to this point is coming from somebody walking at that point there, which sort of makes sense. We can look at these vibrations in more detail as well using the chart views. View chart views, footfall analysis. Let's call these charts of the various modes, and we say response is oh, mine's gone right. Let me type that down there so I can actually read it. Right, view, chart view, footfall analysis. Take those two. Response node 2871, 2763. Walking speeds 2.2. And we can see the various charts, for example, the transient modes which are important. Transient vibration over time, the transient response in relation to the walking frequency is interesting. This is a small kink, which is unusual, but we're talking about remote vibration, so it's unexpected. The resonant analysis, again, which modes are critical for the resonant analysis. The forcing functions, which are standard, these come from the design codes. This is the harmonic forcing frequency against response, and the most interesting one is the walking frequency against response. And you can see lost the general analysis, which is up to 2.5 Hz. The peak response is actually coming from somebody walking at about 1.85 5 Hertz. But you can see you do get peaks at particular points, and sometimes reducing the maximum walking speed doesn't actually reduce your response values, because it might not be the highest walking speed which is actually governing the results there. So, okay, conscious of the time, summary. Use GSA to find the vibration modes, whether it's steel, concrete, stair, bridge, whatever. Find accelerations, the responses, and so on, and drill down in more detail in the output and the chart views